In this video, we'll consider the class of undamped oscillators with a periodic forcing function m times u double prime plus k times u equals f naught times cosine omega t, where f naught equals f of 0 is the initial force, and where omega is the frequency of the forcing function. To find solutions to this non-homogeneous differential equation, we first look at the associated homogeneous differential equation m times u double prime plus k times u equals 0. This we already studied, and we found the solutions in terms of omega naught equal to the square root of k over m in constant c1, c2 to be u of t equals c1 times cosine omega naught t plus c2 times sine omega naught t. Given the form of the non-homogeneous function g of t equals f naught times cosine omega t, we know that the particular solution will have the form u sub p of t equals a times cosine omega t plus b times sine omega t, and that we can write this as a single periodic function r times cosine omega t minus delta, where we're defining r to be the square root of a squared plus b squared, and the tangent of delta to be b over a. But I want to note that this is not the particular solution if omega is equal to omega naught. That is, the frequency of the forcing function, omega, is the same as the natural frequency of the mass spring system, omega naught. In this case, where omega is equal to omega naught, the particular solution has the form u sub p of t equals t times a cosine omega t plus b sine omega t, which similarly can be rewritten as r times t cosine omega t minus delta, where r again here is the square root of a squared plus b squared, and the tangent of delta is b over a. If we consider the long-term behavior of this particular solution, we can see that as t increases, so does the amplitude r times t of the particular solution, and thus of all solutions to the differential equation. So if the forcing function has the same frequency as the natural frequency of our system, the solutions will get larger and larger and still oscillate periodically. This phenomenon that happens when the forcing frequency is equal to the natural frequency, omega is equal to omega naught, is called resonance and is important to consider. In structural examples, such as bridges and buildings, we need to be mindful of resonance because it can be so destructive to these structures. However, there are also cases where resonance can be beneficial. For example, microwave ovens send out microwaves at the same frequency that water naturally vibrates at. This is what causes the water in our food to heat up. So resonance can be a very powerful tool or a very destructive consequence, and should be taken into consideration in all applications with periodic forcing functions.